Solar fruit dryer. Okay, so the reason we're doing this project is to battle hunger in starving villages in Mikuni County, Kenya. And with research we found that in Mikuni County about 24% of the villagers are underweight as opposed to the Kenyan national average, which was 15%. And compare that to the US national average, which was about 2%. So you can see this is a really big problem in Kenya. And the reason, or how we're going to fight this issue is by preserving the nutrients in fruits by dehydrating them. And dehydrating the fruit does many things. It prolongs the lifespan of the fruit, it provides a surplus for the entire year, and it combats with the drought season.
Hey, you can't park that!
Anyway, during the research phase, we realized that there are some conditions specific to Mikuni County that help us come up with our design criteria. Those conditions are poverty, average temperature, humidity, and doctor per population ratio. We put side-to-side comparison between said conditions in Arizona versus Mikuni County to give you a better picture. Finally, we want our final product to be low-cost, self-sustaining, effective, efficient, and sanitary.
Let's take a look at the fruit drying process! Okay, so what do we need? We need humidity to be below 60%, a temperature that's higher than 80 degrees, and we have to keep in mind that it is a slow process, so hygiene is very important.
Prototype considerations. Chair.
Chair, yeah!
Pros. Maximum sunlight exposure. Cons. Not enough volume. Overall, sucks. Chimney.
Yeah, chimney!
Overall, pros. Maximum protection for the fruit. Cons. Not enough sunlight.
Boo!
Overall, sucks. Shelf.
Woohoo, shelf!
Mix between the two. Overall, sucks less.
Best of both worlds!
So just in case you didn't believe our reasoning on the last slide, this shows you the numbers behind our decision. As you can see, the chair and the chimney were pretty close in their total value to our goal, but in the end, the shelf was the winner at 64 total. Estimated budget was $160. However, we ended up spending only about $59, so we're a little over $91 under budget. No! Under budget.
The last aspect of our design is maintenance and hygiene considerations. For maintenance, we wanted to essentially build a self-sustaining product that the Kenyans would be able to keep going after we shipped it, because we won't be able to fly out there and fix it for them every time there's an issue. Also, we had to consider hygiene because we don't want to be making a product that's going to kill the people that are using it.
Whoa!
So, the first point that we decided to address was what's going to make our product water resistant. So we're looking at applying a non-toxic oil-based coating, something like you would put on a cutting board, finisher sort of thing like that, that would keep the wood protected from the elements, but also not damage the fruit. We tried to keep this design as simple as possible, that way if anything goes wrong or breaks, people will be able to replace the parts easily. And then also we're going to be including an information sheet with final product delivery, in which we will include a materials list and the construction process. That way they will see how we built what we built, and they can implement it in their own fashion if they need to. And then operation instructions, so that they will know how they should be using our design to dry fruits the way that we intended it to be used. And then general hygiene habits, so that they know how it is they should be using our products so that they don't get other people sick.
Okay, prototype testing procedure. Okay, so there are two parts to our prototype testing procedure. Hold on, I have to pee.
Alright, so where was I? Right, testing procedures. Okay. So our testing procedure consisted of two parts. The first part was just to see how much water was in each fruit, and the second part was actually testing with the prototype. Okay, so the setup part, we had to use an oven to see how much water was in each fruit, and we did this by slicing each fruit into a 1/4 inch thickness, and then we measured the mass of the conglomerate slices, then we dehydrated the fruit by putting it in the oven, and then we checked the mass periodically until the mass stopped changing, and then we measured that mass and we subtracted the final mass from the initial mass and then divided by the initial mass and then multiplied by 100 to estimate the water percentage.
Smells like wet dog in here. Sorry, that's me. Anyway, we then put the fruit into the prototype and tested it with the same size slices. We put each type of fruit on every shelf so that we could keep that controlled. Then we used the numbers from the setup portion of the testing procedure to see how well our fruit dryer was working. So, based on our setup procedure, we found that the mango was about 85% water, the apple was about 86% water, and the cassava was about 60% water. As you can see on the slide, that the solar dryer was able to dry comparable amounts of water from the fruit as the oven was. So, we also needed to determine whether the fruit at the bottom shelf would dry at a comparable rate to the fruit at the top shelf. So in order to do this, we measured the rate at which each type of fruit dried on each specific shelf. However, we ran into problems when the top shelf tinfoil blew off, and we were no longer able to collect this data after the first interval. So, this is something we will need to repeat next semester.
Let's look to the future! Ha-ha!
For possible future improvement, we want to try to open up our design to allow more airflow. Every part that seems to be open in this drawing will be replaced by metal mesh, just like the one you can see in the back side of the drawing.
Don't believe us? Well, we got 8 sources that back us up.